Have you ever wondered how a machine actually thinks? Well, today we're going to rewind the clock, go all the way back to the very beginning of artificial intelligence, and meet the original digital brain cell. I mean, this is the question, right? It's what drives the entire field of AI. So let's just forget about all the super complex algorithms for a second and think about the most basic decision you can make. Yes or no? On or off? True or false? How do you actually teach a pile of code to make that simple choice? And the answer, believe it or not, starts right here, with one simple, elegant concept that was modeled directly on the neurons firing inside our own heads. This is the story of the perceptron. So what is a perceptron really? Well, it was one of the very first and simplest models of an artificial neuron. You could call it the hello world of neural networks. It's the little seed that almost everything else in modern AI grew out of. Okay, so how does this little digital brain cell actually do its job? Let's pop the hood and take a look at its core parts. First things first, it needs info from the outside world. We call these the inputs. In a real neuron in your brain, this could be light hitting your eye. For our digital neuron, it's just data, any piece of information we want it to think about. But here's the thing, not all information is created equal, right? That's where weights come in. Think of them like little volume knobs for each input. If one piece of info is super important for making the right decision, we crank its weight way up. If it's kind of useless, we turn it way down. This is absolutely key for learning. And finally, you've got the bias. The best way to think about this is like a little thumb on the scale. It's just an internal nudge that makes the neuron a bit more or a bit less likely to fire, no matter what the inputs are. It's just one more knob we can tweak to get the decision just right. All right, so let's put it all together. The inputs come in, each one gets multiplied by its own special weight. Then we just add all of those weighted inputs up, throw in the bias for good measure, and that final number gets pushed into something called an activation function. For our simple perceptron, that function is basically just a gatekeeper. Is the final sum bigger than 0? If it is, bam, it fires a 1. If it's not, it stays quiet and outputs a 0. And that's it. That's the whole process. And that entire flow, weighing the inputs, summing them up, and then deciding to fire, can be boiled down to this one beautiful little equation. This is the perceptron's entire brain, its whole logic, right there in that one simple rule. Okay, so it can make a decision. Cool. But how does it learn to make the right decision? This is where the magic really starts. It learns from its mistakes by slowly, carefully adjusting those weights and that bias. So let's give our brand new perceptron a simple little job to do, learning the AND logic gate. The rule here is super simple. The output should only be 1 if input 1 and input 2 are both 1. For every other situation, the answer is 0. So the whole learning thing just becomes a simple game. We show our perceptron an example, it makes a guess, and then we check its guess against the correct answer. And the most important piece of this game is the error. It's literally just the difference between the target, what the answer should be, and what the perceptron's output actually was. If the guess was right, the error is 0. We're happy. But if it's wrong, that error is the signal that tells the machine, hey, you need to change something. And that brings us to the learning loop itself. It's this constant cycle. We show it an example, it spits out a prediction. If that prediction is wrong, we use that error to give the weights and the bias a tiny little nudge. Then we just do it again with the next example and the next and the next until it can go through the whole list without making a single mistake. So after all that training, after that whole learning loop, what has our perceptron actually learned how to do? What's its core skill? It really helps to see it visually. And this, right here, is it. The perceptron's one and only superpower is this. It learns how to find and draw a single, straight line that perfectly separates one group of data from another. It draws a line in the sand. We call that line a decision boundary. For our little AND gate problem, the perceptron learned exactly where to draw a line to fence off that one case where the answer is 1 from the other 3 cases where the answer is 0. Anything that falls on one side of the line is a 0. Anything on the other is a 1. Simple, powerful, and for a lot of problems, it works perfectly. But you know how this goes. Every superhero has a weakness. And for all its simple power, the perceptron has a really famous one, a real piece of kryptonite. It's called the XOR problem. XOR stands for exclusive OR. The rule is the output is 1 if one input or the other is one, but not if they're both one. And this really simple little logic puzzle completely breaks our perceptron. Why? Because the data isn't, as they say, linearly separable. Just look at the data here. Try it yourself. Can you draw one single straight line that separates the two groups? No way. You can't do it. It's impossible. And if a human can't do it, a single perceptron can't do it either. This simple realization was like a bombshell in the early days of AI. It was so profound, it actually helped kick off what became known as the first AI winter, when a lot of research just stopped. But here's the twist. That limitation, that failure, it wasn't a dead end. In fact, it was the exact opposite. It was the crucial wake-up call that pushed the entire field of AI forward. So let's just recap. The perceptron is awesome for any kind of yes or no problem where you can draw a clean line between the two answers. It's the foundation for everything from simple spam filters to the individual neurons in today's giant AI models. But its big weakness, its kryptonite, is that it can only solve those kinds of linearly separable problems. And this all leads us to the final critical question. The perceptron's limitation forced the pioneers of AI to ask, okay, what's next? If one lonely neuron can draw one simple line, what happens when you start connecting thousands or even millions of them together? Well, the answer to that is modern deep learning. It's the engine that's driving the